Well, hello 403. Um, let's start off. I just finished my redo of the inductors. Now we're going to go into taking a look at our op-amp circuits. So what we've got, first we're going to consider a simple op-amp circuit. We've got some type of voltage input. I'm just going to call it V, set to ground. It's going to come in, and instead of having a resistor here, which we're used to, minus plus, set to ground, out. All right, we'll take a look at what will look like a normal thing for doing an inverting amplifier. So if we had the same thing, if I had a resistor here, you would just think, hey, inverting amplifier, ratio resistors, away we go. But now I've got a capacitor, and what's going on here? Now, a first thought that you should consider when you're looking through this is think of this in terms of kind of an intuitive analysis of what's going on. This voltage source, let's assume that it's got a time varying signal. If it's not, this is a very trivial circuit, because if it's a DC circuit, it's going to come, hit this capacitor. DC values cannot pass a capacitor, so boom, we're done. The signal becomes zero, and this becomes, kind of a ground. Nothing is driving this at all, and the signal is all over with. So, away we go. There's nothing that's trying to happen here. No current flow is going, so you're not going to pull any current flow back here. So the whole thing is just off. So DC is not going to pass, but higher frequency ones will pass through. So this actually is an example of what is going to be a high pass system. Low frequencies don't go through. High frequencies will. High frequencies go through perfectly past the capacitor. Actually, the higher the frequency, the easier it will move through. So this is a first order high pass filter. Now this has a second function that goes on that becomes apparent when we take a look at the equation. So we should look at this though, and our first thought should say, this is high pass. I say it's first order because it's just a simple first order system that's on here. This is akin to what you would get with a simple first order high pass filter, which just looks like that, where you have your V in and your V out. And indeed, you can actually do this to use the circuit we're going to go on and build today. It's just not as stable, it's not as reliable, things like that. So this is a much better way both to do the high pass filter. It is more active, so it doesn't have some of the nice passive feature that goes on with it, but it actually will do the job much better, much cleaner, and it will handle what we're going to try to do here. I'm deliberately trying to avoid saying what is advanced because I want it to come out in the equations. So we've got a node here. So if we have a node, let's do the node law. So the node law is going to require taking a look at the currents flowing in. This it's on the minus one, so we call it V minus at that point. That's going on. So V minus, and I've got to consider the current through here. Right? I've got my difference, V minus minus V. Now, if you remember, for a capacitor, we have Canadian Velvet is the queen of beers. We have to actually take the derivative, so we get CV dot is equal to I. Now I've got my thing for current, but it takes the derivative. To show derivative here, I'm just going to do ddt, do Leibniz notation. We'll assume C is constant because we're not using things like a condensing microphone or things like that, which is basically the old style microphones you'd see in like the 40s and stuff. Very high quality actually, but they work on parallel plates, and your sound moves the plates and changes the capacitance, and that's how they read out the sound that's been recorded. So this is the current that's flowing through here. I get the current through here. That one is just basic Ohm's law stuff. So I get V minus minus V out all over R. That's got to be equal to the current that's flowing into here, but we assume that's 0 for an ideal op amp. It should be pretty darn close to 0 anyway. Now V minus has to equal V plus, and V plus is grounded, so those go to 0. So this kind of simplifies up. I've got a negative, so I'm just going to clear through the negatives. So I end up with C, and I get V dot plus, and I've cleared the negatives, so I just kind of multiply through negative on the whole thing. That's 0, so I end up with V0 over R. That has to equal 0. So now I get C. Oops, I'm just going to do this in one fell swoop. We'll just do V dot. Is equal to, oh, I want V0. Sorry. V0 is equal to, and then I'm going to multiply through by R, take that to the other side. I get minus RC V dot. This is your time constant tau. Alright, but that's just a scalar as far as we're concerned. It's inverting, standard negative input type situation. So we see that's an inverting signal. But these are both just constants that go on. What we really see that's interesting is I've got the derivative of the input to the output. So my high-pass filter does differentiation. How to understand this as what is. I mean, it is what it is, right? I mean, so one level you could do it without understanding. This is a differentiating circuit. But differentiating is high-pass. I'm going to borrow a result from what's going to happen later on in the course. And later on in the course, you're going to see things that have to do with frequency transforms. Let me just steal a little piece of the paper here. Consider sine of omega t. Now let me take the derivative of sine of omega t. Well, that's got to be equal to, well, derivative of sine is cosine. And then the inside, I take its derivative, I get omega. So if you look at this, when I take a derivative of a function, I get a phase shift of that function. And this is just a phase shift going on to go from sine to cosine, but I have an amplitude magnifier. If omega is really small, that'll be multiplying by a small number. So in essence, low frequency ones, the amplitude gets driven down, so they get killed off. High frequency ones will be amplified, i.e. high frequency lives. So this is a high pass filter. So differentiation becomes a high pass filter. And you might say, well, that works great for sines, but what about for other stuff? Well, this is the result that comes in later on, that we can take the Fourier transform and we can break other functions up into their sine components. And therefore, this is a general result now due to the transform techniques. So differentiation is, luckily, nicely, a high-pass filter. So when you get one, you get the other. And that's why this will work. It's just not as clean as this is, because I have the real high impedance here and the nice properties that come on with op amps. So this gives you the first cut. We'll have to, on the next video that comes on, I will deal with the other one. But this is what we're going to want to build for our first things on Thursday. So hope you're having a good time, and I hope this helped out a little bit. Talk to you soon. Bye.